Chapter 1, Part 5, Isomers and Line Bond Structures. So, isomers are molecules that have the same molecular formula but a different structure. This is specifically a constitutional isomer. So, for example, C2H6O. We looked at this formula earlier when we were talking about the molecule ethanol or ethyl alcohol and the different ways that we could show the formula. So this is ethanol. It has 2 carbons, 6 hydrogens, 1 oxygen. This is dimethyl ether. It also has 2 carbons, 6 hydrogens, and 1 oxygen, which is why the formula C2H6O is not exactly the most useful way to represent a molecule. So if we take a look at these two molecules and compare them, you'll see that in ethanol, the 2 carbons are attached together, and then they have an OH group coming off of it. That's what makes it an alcohol, actually. Whereas in dimethyl ether, the carbons are flanking either side of the oxygen, and it's this structure that makes it an ether. So these are different molecules that are going to have different properties, even though they're going to have the same molecular weight and they have the same formula. Another example, C4H10 is the formula for butane, but you can also take those carbons and kind of rearrange them. So the difference between these two structures is that instead of all 4 carbons being in a continuous chain, we have 3 carbons in a chain and then 1 carbon branching off from the central carbon, which is why this compound is actually called 2-methylpropane. Propane is the word for a 3-carbon structure, and the methyl group, which is a 1-carbon substituent, is coming off of the 2nd carbon. In chapter 4, we'll learn about naming. So let's talk about bond line, line bond, or skeletal structures. All of these words mean the same thing. To draw a bond line structure, you follow the rule a carbon at every end and every bend. Each line represents a bond. Each bend in a line or terminus of a line is a carbon. No carbon C's are written for carbon, so you won't see the letter C anywhere in these structures. And all other elements are represented by their elemental symbol. Hydrogens that are on carbons are not written. Hydrogens that are on a heteroatom, which are atoms that are not carbon, so think oxygen, nitrogen, sulfur, these are going to be written explicitly. Carbon has to have 4 bonds total, so we can infer the number of hydrogens based on the number of bonds drawn. And hydrogens that are needed to show stereochemistry are written out. So a lot of these rules don't make any sense yet because you're not looking at a structure. So let's look at some examples, and we'll save the word stereochemistry for chapter 5. So let's talk about drawing and interpreting bond line structures. I'm going to start with just a really simple molecule. We're going to go with propane. Propane is a 3-carbon molecule, which also has 8 hydrogens. So I want you to notice a couple things about the way that I drew propane. One, that took a really long time, right? For such a small compound, that took a really long time. And since all of our reactions in this class are going to involve organic structures, line bond structures are a way of drawing these so much faster. Also, note that I drew the carbon framework in a zigzag pattern. That's just a habit because I've been drawing bond line structures for so long, and it helps to represent the more accurate angles of the carbon-carbon bonds. The other thing I want to point out is that the rule for bond line structures was a carbon at every end and every bend. So right now, the end of the chain are these 2 carbons if we discount the hydrogens. And then the chain is bending at this carbon. So the bond line structure for propane is simply this, which is much faster to draw and over time becomes really, really easy to interpret as well. Also, remember that we don't draw out the letter C for carbons and we don't draw in any hydrogens. So how are we supposed to know how many hydrogens are on each carbon? Well, it comes down to those bonding rules that we looked at in the middle of this chapter, right? Every carbon wants to make 4 bonds. So if this carbon in the middle has 2 bonds to this carbon and this carbon, let's give them names. We'll say A, B, and carbon C. So if carbon B has a bond to carbon A and to carbon C, that's 2 of the 4 bonds that carbon B can make. So the other 2 bonds that are not drawn explicitly must be hydrogens. So we call these hydrogens implicit because they are implied by the rest of the bonds that are in the structure. Now for carbons A and C, they each have 1 bond drawn out. That's the bond to carbon B. And since we know that these carbons want to make 4 bonds, the other 3 bonds must be to hydrogens. So we can imply that there are 3 hydrogens attached to carbon C. And so we don't have to draw them out. And carbon A. So this is how you draw a bond line structure and how you interpret it. I want to point out real fast what the most common misinterpretation is when students are first learning bond line structures. We know that this is supposed to represent 3 carbons. So when you're drawing your bond line structure, it can be really helpful in the beginning to draw a dot for your first carbon, draw your bond to the second carbon, and draw the bond to the third carbon. Following that process can help make sure that you draw the right number of lines, because a lot of students like to count the number of bonds and then interpret this as a 2-carbon molecule. But this is not accurate. Notice how that structure doesn't even look like this structure. There is only a single bond between the 2 carbons. There's no bend in the carbon chain, and there's kind of no way to imply the number of hydrogens. It would be really confusing. So that's just an incorrect interpretation of line bond structures. So while you're learning how to do line bond structures, you can practice with the dots and practice drawing out different size chains. So get used to the feeling of drawing out a 6-carbon chain. Carbon 1, carbon 2, carbon 3, whoops, carbon 4, carbon 5, carbon 6. And after a while, you start to get used to what these shapes look like, and it becomes really, really easy. So let's do some practice problems. Go ahead and pause the video and take a little time to draw the line bond structure for each of the compounds below. Notice the first one is kind of a freebie since I accidentally did that on the previous slide. Okay, so let's go over these. For the first molecule, which is propane, we have 3 carbons, so our line bond structure is 1, 2, 3. For the next one, I threw in a slight complication. There's a double bond there, so we have to think about how are we going to represent a double bond. But first, let's just draw out the carbon framework. So we have 1, 2, 3, 4, 5 carbons all in a row, and then we have another carbon coming off of carbon number 3. So let's go ahead and draw out a 5-carbon chain. We have 1, 2, 3, 4, 5. There's another carbon coming off of the 3rd carbon. And then we have to have some way to represent the double bond between carbons 1 and 2. Let's go ahead and number these so that we're all on the same page. Otherwise, when somebody interprets the structure, they're going to imply that there are 2 hydrogens on carbon number 2 and 3 hydrogens on carbon number 1, which when we look at our structure, we can see is definitely not true. So we do have to represent our double bond. And it's really very simple. All you're going to do is draw a double bond. So line bond structures are very simple. Don't overcomplicate them. It just takes a little practice. And this is practice that's worthwhile because this is how we're going to draw everything in organic chemistry. Let's look at the next one. We have a carbon, oxygen, carbon, carbon. So this is a 4-membered chain, and one of the members is an oxygen. Well, the rule for heteroatoms was that they are drawn out explicitly, so we have to use the letter O for the oxygen. So here is our carbon. Let's go ahead and number the chain just for clarity. Our carbon is atom number 1. Our oxygen is atom number 2. We have another carbon and another carbon. So this is the structure of the compound above, drawn out as a line bond structure. Okay, so let's go the other way. Let's take these line bond structures and draw out the Lewis structures. And I think already you're going to start to appreciate the simplicity of a line bond structure when you have to draw out all of these carbons and hydrogens. So go ahead and pause the video and take a second to do this yourself. Okay, let's draw this out. So in our first compound, we have an oxygen to a carbon, to a carbon, to a carbon, which has a double bond to oxygen and a single bond to hydrogen. Now we can just go through and add on all the rest of the hydrogens. And if you're not sure if you've interpreted correctly, you can always go through and number things. So I usually only number the carbons, and you'll learn why pretty shortly. Okay, let's look at this structure down here. So it has 1, 2, 3, 4 carbons in a row. And then it has another carbon coming off of carbon number 2. So all the rest of this is just filling out hydrogens. I know that I have to have 4 bonds total to each carbon. So carbon number 1 has a single bond to carbon number 2, which means it's going to have 3 other bonds. And I'm just going to use that same math to fill in all the rest of my hydrogens. And this is why at some point we will stop wasting time drawing out Lewis structures. Okay, last one. We have the molecule cyclohexene, and it has 6 carbons in a cyclic structure and a double bond between 2 of them. Another thing you're going to learn in organic chemistry is how to draw out the majority of geometric shapes. So we're going to put a double bond between those 2 carbons, and then let's go in and fill in all the rest of the hydrogens. So let's start here. This carbon has 2 bonds to other carbons, so it must have 2 hydrogens. And that's going to be true for all of these carbons until we get to the double bond. So this carbon here has 3 bonds already attached to it, so it only has room for 1 hydrogen. And that is the structure of cyclohexene. So the last step to this is that sometimes we have to show things in 3D. You'll notice that the line bond structures are very 2D. They're very flat. There is no 3D shape shown. But these molecules are not flat. They would not lie down flat on a piece of paper. They have a 3D geometry. So we use a pretty simple format here. Anything that is drawn as a plain line is in the plane of the paper being the page that you're drawing on. And then if it's on a dashed wedge, it is behind the plane of paper, or you could say that it's pointing away from you. If it's on a solid wedge, it is coming towards you. It's in front of the plane of the paper. So for example, bromomethane, CH3Br. This is a carbon that has 3 hydrogens and 1 bromine. You may recall from Gen Chem 1 that an atom that has 4 things attached to it is sp3 hybridized and is tetrahedral geometry. So the way that this has been drawn out, the bromine, carbon, and the hydrogen that's pointing upwards are all in the plane of the paper. This hydrogen that is on the dashed wedge is going away from us, is going behind the plane of the paper. And the hydrogen that is on a solid wedge is coming towards us. It is in front of the plane of the paper.